There we go. So today's talk, we're going to start off our season with an absolutely amazing speaker, Professor Nick Cowan, from the Physics and Astronomy department at Amherst College. And before we do that, I want to tell you about a couple of other events that are going to happen coming up soon. Actually first, most importantly, our sponsors. I'd like to thank all of them. We have the National Science Foundation sponsored Materials Research Science and Engineering Center on Polymers. Wow. Let's try that again. Materials Research Science and Engineering Center on Polymers. They're at UMass. The Center for Hierarchical Manufacturing at UMass. The Center for Integrated Quantum Materials at Harvard. And Community-Based Learning, which is out of Mongolia. And now we can go into things that are coming up. A little closer? Is that better? Yes. All right. The next talk, which is going to happen on Monday, October 27th, is entitled, Why Do We Sleep? And that's going to be given by Professor Rebecca Spencer, who's from the Department of Psychology and Brain Sciences at UMass. Some other things that you might find interesting, the OEB Science Cafe is at the Echelon Cafe over in Hadley. That's taking place on October 6th at 6 p.m. Science on Screen, they're going to be showing particle fever, where beforehand we'll have three speakers from UMass, three physicists who are going to talk to you about particle physics. And finally, there are flyers hanging around, or being passed around, for Professor Sheldon Glasgow, who won the Nobel Prize in Physics in 1979, and he's going to be giving a lecture, when is this happening? October 1st. So a lot of fun events coming up, and visit as many as you'd like. Okay, so with that, let's jump right in. And so I'd like to introduce Professor Nick Cowan, who as I already said, is from the Physics and Astronomy department at Amherst College. And he's going to tell us about strange new worlds.
Can the people in the back hear me if I talk like this? No? Okay. Yes? Can you hear me now? Okay. All right, so my name is Nick, and I'm going to talk to you about alien worlds. And so, because it's kind of a provocative title, I have to first tell you what I'm not going to tell you about, and then if you're really upset, then maybe you can leave. But hopefully you won't leave and you'll just ask me really fun questions, because I can actually field questions on all sorts of crazy things. But here's the thing I'm not going to talk about. So I'm not going to talk about little green men. I'm sorry. I'm not a biologist, so I'm not qualified to talk about little green men. And in fact, I can't even talk about pond slime. And so I'm not going to talk about that kind of little green person either. Sorry. Instead, I'm going to talk about the planets on which those green critters might live. And so this entire time, we're going to be talking about planets. All right. And so I know about planets. I don't know about life. I don't know biology. I barely even know chemistry, but I know about planets. Okay. So we're going to talk about planets. And so here's the kinds of questions that you might ask if you found a planet. You might ask, what's it made out of? That's a reasonable question. Is it rocky? Or is it icy? Is it made out of styrofoam? Is it made out of jelly beans or something? How hot is it? Would it be hot to the touch? Would it be freezing cold? Would you die if you went and landed on it? What does it look like? That's kind of the obvious question. Turns out that's pretty hard to do, because the planets I study tend to be really, really far away. They tend to be about 100 light years away. So even with the biggest telescopes, we can't really see much at all. But if you guys don't ask enough questions, I might actually get to the part of my talk where I tell you how we can figure out what these planets look like. And then if you guys really don't ask very many questions, then I'll get to, could you breathe the air? And how do you figure out what's in the atmosphere of a planet really far away? At this point, I should just remind you, in case you don't already know, that you guys should feel free to interrupt me and ask questions at any point. And so you can try and raise,
How did you get interested in this topic?
This is a good question, and I will offend, can I really need this? Are there any nuclear physicists in the room? I saw one little hand go up. I don't believe you're a nuclear physicist. You're far too young. You can't possibly be a nuclear physicist
That's a
yet.
good question.
Okay. Oh, you had a question. Okay. I'll get your question in a second. Okay. So since there are no nuclear physicists to offend in the room, I can tell you that the reason I ended up in astronomy and studying planets orbiting other stars. Should I turn this thing off in some way? Whoa. Is there a way to turn this thing off? What's that? What, if I... Okay, but is there a way to just like turn it off if I speak loudly? No? Okay, I just hate microphones, sorry. Okay, so how did I end up interested in extrasolar planets orbiting other stars? Okay, so basically I was studying nuclear physics, and I liked everyone that I worked with in nuclear physics. So I was studying the insides of atoms, the very hearts of atoms, and it was a pretty good job. But all the old people I talked to in the field told me I should really think about something else for my future, because they said a lot of the important questions in nuclear physics had been figured out a really long time ago. And if I wanted to make an impact, I should go into some field where no one knows what the heck is going on. And they suggested maybe you should go study planets around other stars, because they were just being discovered at the time. And so that's what I did. I went and got a PhD studying planets orbiting other stars, of which we knew basically nothing. We still know practically nothing. And so that's how I ended up studying exoplanets. All right, the lady, there were at least two questions over there. This is a very good question. So the question was why I even brought up the pond slime and the little green men if I wasn't going to talk about them. And the answer is that I used, the title of my talk was Alien Worlds. So I was using alien as an adjective, which means it's a word that you use to kind of like do something to the next word, which is worlds. So my talk is about worlds, i.e. planets, and sometimes moons, but mostly planets. And so I was using alien to describe the worlds, because they're weird. A lot of these worlds are completely freaky. They're not at all like any planet you've ever heard of. So I use the word alien, but then people hear alien and then they think little green men. So I just wanted to like make that clear that I wasn't going to talk about little green men. Is that a satisfactory answer? All right, second question.
Is it possible to live on a gas giant in the atmosphere and all the others?
How many planets are there total?
How many planets are there total? Okay. Well, that's a very good question. I don't bother keeping track of that. That's kind of it's a moving target, because there's new planets being discovered every day. And so some of you might recall when Pluto, so the older people in the room might recall when Pluto used to be called a planet. And then we had a vote, and the astronomers had a vote. They had a big powwow, and they voted on this, and they kicked Pluto out of the planet club. And at the time, a lot of people were really offended by this, because they said, no, I learned that Pluto was a planet, which I think is complete hogwash, because by the time Pluto got kicked out of the planet club, we'd already discovered hundreds of planets orbiting other stars. So at that point, you know, this debate of whether there were 8 or 9 planets was ridiculous, because at that point the real number of planets that we knew of was already in the hundreds. So it was, whether it was 345 or 346, like who the heck cares? Because by the next day it was 370, right? And so the number just keeps growing. And today the number is in the thousands. So we know of thousands of planets orbiting stars, only 8 of which orbit our sun. And most of those planets orbiting other stars look nothing like the planets we have in our solar system. All right, so our solar system is not particularly, it's not unique in the sense that there's lots of other planets out there, but on the other hand, most of those planetary systems we've found so far don't actually look like ours. All right, I'm gonna move on to my next, oh wait, there was a question in the back. I'm gonna get that question, and then I'm gonna move on to the next slide, just to keep making progress. Yeah?
Is it possible to live on a gas giant if all the other conditions were right?
Well, if all the other conditions were right, then sure, but that's a pretty big if. So I mean, there's definitely places in gas giants where the temperature is temperate, And there are places in gas giants where both the temperature and the pressure are reasonable. So if you had birds that never had to land, maybe they could live in a gas giant. But it wouldn't work so well for us. And it's not clear that life could evolve on a gas giant. But I'm sure, well, in fact, I'm quite certain that people have written scientific articles about this, and I'm even more certain people have written science fiction books about this. Okay. So if we want to figure out what a planet is made of, the first thing we want to figure out is how much it weighs. And so when we want to weigh something, well, the way we do it on Earth, and you don't necessarily think about this every time you weigh yourself, or you weigh, flour in this case, but what you're actually doing when you're weighing something is you're measuring how much that object is attracted to another massive object, which is the Earth. Okay, so you're basically taking yourself and you're measuring how much attraction your body feels to the Earth and how much attraction the Earth feels to you, right? So it's whatever it is, 180 pounds, right? So the Earth feels that attraction. The Earth is being pulled towards me by 180 pounds. Okay, so that's how scales work. They measure that using a spring inside. It turns out we can't send a scale to a planet that's 100 light years away. So what do we do instead? Well, we use the only object that there is next to the planet, which is the star that it orbits around. And so then you get something that looks like this, where you have a star, that's the yellow circle, and then you have a planet that you can't see, right? So that's why it's called unseen planet. And there's light from the star that's coming into your telescope. And the thing you have to know is this thing called the Doppler effect, okay, which a lot of people are familiar with their ears, okay, which is the way like the siren of an ambulance or something changes when it zooms by you, right? So when it's coming towards you, the waves, the sound waves are all scrunched together, and so it sounds high pitched. So it goes wee wee wee, and then just as it passes you, it goes wee wee wee, like that, and it goes and it's low pitched because then you're stretching out the waves. All right, so it turns out light does the same thing. So when the star is receding away from you, it stretches out the light waves, and then they look redder. You just have to take my word for it that stretched out light waves look red. And when it moves towards you, it looks bluer, okay? And the key thing is that this is a very, very subtle effect. So if I move back and forth like this, I do not, my color doesn't change, right? You guys don't see me changing color. And that's because, well, it's for two reasons. One, I'm not moving anywhere near the speed of light. So if I was moving near the speed of light back and forth, I actually would appear to change color, but I can't do that. But it turns out stars wobbling around because of a planet move at exactly this pace. They move kind of like 1 meter per second for those of you who know metric. Okay, so it's like a walking pace. All right, so that's the rate at which stars wobble back and forth. And it turns out we can actually detect that, even from tens or hundreds of light years away. We can detect it from super far away with our telescopes. And the key is that the colors change just a little bit, but we can actually detect that tiny change in color. All right, so this is how we weigh planets. Okay, we look at the star wobbles around, and the more the star wobbles, the more we know that it's attracted to its planet, and that tells us that that planet must be very massive, must have a lot of mass. Okay, it's a big planet. Okay, so now here's my chart number 1. This is for the adults in the room. The kids, you can just ignore this. It's just colorful for you. But for the adults, here's kind of a summary of what we currently know about the masses of planets. Okay, so that's sort of how heavy they are. All right, and I've conveniently labeled a few planets that you know. So from the right, that's Jupiter. That's the biggest thing in our solar system. So you can see that there's plenty of planets out there that we know of. Okay, in fact, there's hundreds of planets that we know of. They're about the mass of Jupiter. So that means Jupiter is a pretty typical planet. Then there's Saturn, because it's got rings. That's Neptune. The blue one is Neptune. And then Earth is the furthest left one. All right, and so you might be worried that there's like Earth is hanging on the side of this cliff, which means that there aren't very many things the size of Earth, and there appears to be nothing in the universe that's smaller than Earth. But don't be afraid. It turns out everything on the left-hand side of that plot is very suspect, because those are really, really, really hard planets to detect, because they're so small that the star barely moves. Okay, so when the planet is orbiting around the star just basically sits there, and so it's really hard to even figure out that those planets are there. So the ones on the left-hand side are the tricky ones. Yeah?
She was actually ahead of me, but I have a question too.
Okay. Yes?
Danielle, it's your turn.
You ready? Can someone relay that question over? I can't hear that. What's the moon made of? Yeah, the moon is made out of rock. It's actually made out of pretty much the same sort of rock that our crust is made out of. So the rocks that you walk around on Earth is fairly similar to what the moon is made out of. The moon is actually, it's kind of too similar. It's sort of suspicious how similar the moon is to the surface of Earth. And so one of the fun things about the moon is that our best guess as to how the moon got there is that a big rock smashed into the Earth and basically made kind of a ring around Earth, just like Saturn has, and eventually that clumped together into our moon. And so the moon is like quite literally made out of the same stuff as the Earth, because it used to be, there was a brief moment there where we were all one happy family, but it hit us too fast and we all blew apart. So now we have a moon and the Earth made out of basically the same stuff. It's not made out of cheese, that's for sure. Yes?
So, granted that the left corner is not accurate, but it's like two bell curves. Why are there two bell curves like that? Why is it a dip?
Yeah, this is a great question. Yeah. Oh, sorry. Yeah. The question was why there's a dip in the middle here, right? So it looks like if you look at the kinds of planets that our universe makes, she likes to make planets that are kind of like Neptune size or smaller, and planets that are kind of like Saturn and bigger, but there's a dip in the middle. And this is still an area of active research. There used to be a really nice story that explained exactly how the 8 planets in our solar system came to be, and that prediction was wrong for this. And so this kind of sent all the planet formation people back to the drawing board. But the kind of one sentence answer is that it has to do with how big a planet has to be before you can start sucking lots of gas onto it. So Saturn and Jupiter are mostly made out of gas, whereas the stuff on the left-hand side, Neptune, Uranus, Earth, Mars, Venus, all those planets are mostly made out of rock and ice, out of solid materials. So that's the basic difference. That cut in the middle of the slide there is basically dividing things between gassy planets on the right and kind of rocky, icy things on the left.
So if it's too heavy, it starts to just form a gas giant? Is that the idea?
Exactly, yeah. If you get too heavy, then there's lots of gas. When planets are forming in the early days, there's lots of gas around. And so if you get too heavy, then you just start sucking gas onto you. And that's sort of this runaway effect. And next thing you know, you're like the size of Saturn or Jupiter, and you're basically made out of gas. There was another question.
Yeah, I was wondering if the composition of planets, like what they're made out of, is related to their distance from the sun.
This is a great question. Is the composition of planets related to their distance from the sun? Well, certainly in our solar system, it's the case that all the planets that have a lot of gas on them are far from the sun. And this was something that had a very neat explanation back in the day, which I will not bore you with, because whatever that explanation was is clearly wrong, because I don't even know whether I have the right slides exactly to show you, but suffice to say that most of the planets we know of now are big gassy planets in really, really close to their star. So clearly, whatever we have in our solar system is not necessarily the norm. It's not necessarily, the only way planets can form. And so it's one of the ways in which planets can form, but clearly there's a whole plethora of other ways in which planets can form that don't look like our solar system. Yes, in the front, young lady. How does a telescope see so far? All right. So one of the popular answers people throw out, which I will suggest to you, and then you can explain to me why it's wrong, is that telescopes are on top of mountains, and when you go up on top of a mountain, you're getting closer to the stars. Do you know why that's wrong? What's that? Well, yeah, this is a good point. A, telescopes aren't always on mountains. They're sometimes in deserts. B, the stars are so far away that going on top of a mountain doesn't really help you much at all. So the reason you want to be on top of mountains often is because you get above a lot of our atmosphere. So have you ever seen pictures of people climbing like tall mountains in the Himalayas, like Mount Everest? And sometimes they would wear oxygen masks, right? And they do that because there's so little air up there that it's hard to breathe. Right. Well, it turns out, and also if you see pictures from the high mountains, you'll see that the sky is very, very dark. It's almost black, even during the day. All right, instead of being blue like it is here, and that's because the air is so thin, it barely scatters any light towards you from other directions, right? So it's almost like you're going into space, just being on top of a mountain. And that's very convenient because the air is our enemy for astronomers, because we have to look through our atmosphere, and the air has a lot of issues with it. It moves around and absorbs light, and suffice to say that you're better off, ideally you just send your telescope into space. And so I'm going to talk about a few telescopes later on that are space telescopes. Those are my favorite telescopes because then you don't have to deal with our atmosphere at all. But the poor man's space telescope is just to go to the top of a really tall mountain where the air is really dry and cold, and then you put a telescope there. So that's one of the reasons. The other reason is that telescopes are really big, right? If you think how your eye sees, you've got a tiny little hole in your eye, right? And so you can only collect light through that tiny little hole. Well,